Why hybrids use a completely different engine, Atkinson cycle, weird compression, less power on paper, and why that actually makes them better for what they do. Everyone knows hybrids have batteries and electric motors. Very few people realize the gasoline engine under the hood is not the same as the one in a normal car. Look at the specs, and you'll see it. Same displacement as a regular engine, less horsepower, different compression ratio, and buried somewhere in the brochure, Atkinson cycle. So what is that? Why did engineers deliberately build a weaker engine and then call it an upgrade? And why does it matter so much for Prius, Camry Hybrid, RAV4 Hybrid, Accord Hybrid, CR-V Hybrid, and the rest? I'm GearHead. I don't care about buzzwords, I care about what's happening in the cylinder, gas exchange, pressure, combustion phasing, and how that turns into efficiency, reliability, and real-world behavior. If you want to understand hybrids at that level, make sure you're subscribed. This is exactly the kind of small detail that quietly separates a good hybrid system from a bad one. Let's break the Atkinson cycle down in plain language and why hybrids need it. First, remember what a normal engine is doing. Most regular gas engines today are Otto Cycle engines, named after Nicholas Otto, even if they've got all kinds of modern tech on top, VVT, direct injection, turbos. Very simplified Otto cycle, intake stroke, piston goes down, intake valve open, cylinder fills with air, and fuel in port-injected engines. Compression stroke, intake valve closes, piston moves up, compressing mixture. Power stroke, spark plug fires near top dead center, combustion pushes piston down. Exhaust stroke, exhaust valve opens, piston pushes burned gas out. The key thing, the compression ratio and expansion ratio are basically the same. If you compress from volume A to B, you expand from B back to A. High compression ratio equals more thermal efficiency, but also higher cylinder pressures, more knock tendency, pinging or pre-ignition, and more stress on parts. That's why high-performance auto engines need good fuel and careful tuning. They're walking a line between power and detonation. Now, hybrid engineers looked at this and said, okay, we don't actually need max power from the gas engine in a hybrid. We want max efficiency. We've got an electric motor to fill in the torque gaps. Enter the Atkinson cycle. What is the Atkinson cycle? The original Atkinson engine from the 1800s used a funky mechanical linkage to have a shorter compression stroke and a longer expansion stroke in one full cycle. Modern Atkinson cycle engines don't use crazy linkages, they cheat with valve timing. Instead of physically changing stroke length, they use late intake valve closing, ILCV, to shorten effective compression while keeping the actual expansion stroke the same length. Here's how a modern Atkinson engine, like in Toyota and Honda hybrids, behaves. Intake stroke, piston goes down, intake valve open, cylinder starts filling with air. Compression stroke, piston comes up, but the intake valve stays open longer than in an auto engine. Some of the air that was drawn in gets pushed back into the intake manifold. Mid-compression, intake valve finally closes. Only then does real compression start from a smaller trapped volume. Power stroke, combustion happens, piston pushed down through full stroke. Exhaust stroke, same as usual. Result? Lower effective compression ratio because you started compression later. Expansion ratio is still high because you still expand over the full stroke. You're doing lower compression of a smaller charge plus full expansion of that charge, which is more like the original Atkinson idea. Long expansion, short compression. Why do this? Because thermodynamically, more expansion for a given amount of compression means better ability to convert combustion energy into useful work instead of waste heat. In simple terms, you squeeze less, then you stretch more, and you get more efficiency out of the burn. You end up with higher thermal efficiency, better percentage of fuel energy converted to mechanical work, lower peak pressures, good for durability and knock resistance, and less torque and power per liter because you're effectively throwing some intake charge back out. That's why a 2.5-liter Toyota Atkinson engine might make around 170 to 180 horsepower, whereas a 2.5-liter Otto engine might make 200 to 210 plus horsepower. You lost power, but you gained efficiency. So why does that work so well in hybrids specifically? Because hybrids have electric motors bolted in. Electric motors are the masters of low RPM torque. They deliver peak torque from near 0 RPM, respond instantly, and don't care about compression ratios or flame speeds. An Atkinson engine by itself feels soft at low RPM, less cylinder fill, lazy off the line compared to an Otto engine of the same size. Hybrids fix that by letting the electric motor handle the situations where an Atkinson is weak, starting from a stop, low-speed acceleration, filling in torque when you mash the pedal. So the hybrid gets an engine optimized for sipping fuel when it runs, and a motor optimized for shoving the car around at low speed. Together, engine equals efficient generator/highway/steady unit, motor equals launch/assist/regen unit. That's the core reason hybrids don't just drop normal engines and call it a day. The whole point is if you're going to lug a battery and a motor around, make the engine itself as efficient as you can, not as powerful as you can.
Let's talk a bit more about thermal efficiency, because this is the metric hybrid engineers obsess over. A decent Otto engine might have peak thermal efficiency in the low to mid 30% range. That means only 30-something% of the chemical energy in fuel becomes mechanical work. The rest is heat loss through exhaust, coolant, friction, etc. Modern Atkinson Cycle hybrid engines from Toyota and Honda have reported peak thermal efficiencies of around 40 to 41%, Toyota's newer 2.5-liter and 2.0-liter hybrids. Similar numbers claimed by Honda in their latest two-motor EHEV systems. That's a huge jump in engine-only efficiency. When you add clever hybrid control, you can keep the engine operating closer to those efficient points more often. That's how you end up with Priuses doing 50 to 60 mpg in mixed use, Accord and Camry hybrids comfortably in the 40s to 50s mpg, RAV4, CR-V, and Highlander hybrids getting astonishing mpg for their size. The Atkinson cycle is one of the most important pieces of that puzzle. You might be wondering, if Atkinson is so great, why don't we use it on all engines? Because everything is a trade-off. Atkinson Pros, better efficiency, lower knock tendency, you can run higher geometric compression ratio because effective compression is lower, gentler on components due to lower peak pressures. Atkinson Cons, lower torque per liter, worse feel in a non-hybrid car, especially at low RPM, needs help to deliver strong performance across the rev range. In a non-hybrid, if you make it Atkinson, you have to either make it bigger, more displacement to get the same torque, or accept a much lazier engine. Both hurt packaging or marketing. People want numbers on the brochure. In a hybrid, the electric motor solves the low-speed torque problem, so you can afford to go Atkinson and accept that on its own the engine would feel weak. It's a complementary design. Otto engine by itself has to be everything. Idle, launch, cruise, peak power. Atkinson engine in a hybrid can be one thing, efficient when running. The motor covers the rest. Where do VVT and pseudo-Atkinson come in? Some car makers cheat a bit. They use variable valve timing to create Atkinson-like behavior at some loads and more Otto-like behavior at others. Late intake valve closing is VVT controlled. That means under light load, close the intake valve late, Atkinson-ish, efficiency. Under high load, close it earlier, more volume trapped, Otto-ish, power. Toyota and Honda both use sophisticated VVT strategies to make their engines flexible, but in most hybrids they stay biased hard toward Atkinson behavior, because again, power is less important than efficiency, and the motor can fill in. This is why you'll sometimes see Atkinson Otto Cycle switching language in technical papers, but in practice, in many hybrids, it's basically an Atkinson workhorse hardened by VVT. What about durability? Does Atkinson help or hurt? From a durability standpoint, Atkinson actually helps in a few ways. Lower effective compression, lower peak firing pressures, less pounding on rods, bearings, and pistons, smoother, more predictable engine speed profiles in hybrid duty, especially in Toyota's HSD where engine RPM is often controlled around efficiency points, less reliance on turbocharging in many hybrids, many Toyota hybrids or NA, which means fewer heat soak issues, simpler exhaust hardware, lower specific stress. Combine that with the fact that the electric motor is doing a lot of the violent stuff, jerky, stop and go, instant torque at 0 RPM, and you get a recipe for very long life.
That's how you end up with Prius engines opening at 200 to 300,000 miles that still look remarkably clean inside. Camry hybrid motors that wear no worse than their non-hybrid cousins, sometimes better. Hybrid SUVs that aren't beating their engines to death hauling mass from a dead stop all by themselves all the time. The flip side, an Atkinson hybrid engine still dies if you ignore oil changes, overheat it, or let EGR systems choke it with soot. Hybrid isn't a magic shield. Some Atkinson engines, particularly Gen 3 Prius, showed head gasket weakness when cooling and EGR weren't cared for. But overall, Atkinson and hybrid duty is a kinder life on the engine than a small, turbocharged Otto Cycle gas engine in a heavy SUV doing the same daily grind. So, to answer the original question, why do hybrids use a completely different engine? Because they don't need max power from gas, they need max efficiency. The electric motor covers for the Atkinson engine's low-end torque weakness. The Atkinson cycle's longer expansion stroke and late intake valve timing boost thermal efficiency significantly. Lower effective compression stress and under-stressed engineering means long life, especially with a smart hybrid control strategy. An Atkinson engine in a regular, non-hybrid compact sedan might feel disappointing. An Atkinson engine in a well-tuned hybrid feels like part of a system that was designed as a system, not a gas car with a motor bolted on. If this deep dive made Atkinson, valve timing, and hybrid engines are different finally click for you, make sure you're subscribed. Next, I'm going to connect the dots even further and break down how Toyota, Honda, and Hyundai/Kia use Atkinson and motor sizing differently, and how that's why a Prius, an Accord hybrid, and an Ioniq hybrid all feel different even though they're chasing the same efficiency target. I'm GearHead. Every engine cycle has a story, and together we're going to decode why the weird hybrid engines are often the ones you actually want under the hood.